Okay, so today we're going to go ahead and talk about power in physics. So oftentimes when we think of things, we don't care about just like how much work or how much of something was done. We care about the rate or like how fast something was done. So with power, power is just the rate of doing work. And so it is the rate at which energy is either consumed or generated. So I want you to think to yourself, what might be this equation of work? And then check back into the video. Okay, so we know power is a rate. So we know a rate is like per unit of time. So our equation for power is just going to be work divided by time. So it's the rate that we do work. So work per time. Or if we were to write it out, we can say power equals work divided by time with just abbreviations. Cool. So this is our good old power equation, where again, W is work and T is time. And keep in mind, this will only be for constant values of work. Great. So let's go ahead and look at this equation. So there's one other equation for power that we'll oftentimes use that's good for like instantaneous power at a certain moment. So we know power is work over time. We know work is what? Force times displacement. This is all over time. If we look at this equation and rearrange, I kind of think of displacement over time as essentially like average velocity, but if we're looking at instantaneous cases, it'll just be force times velocity. So the other equation that we'll oftentimes use for power is force times velocity, where again, P is power, F is force, which again will oftentimes be measured in newtons, and V is velocity, which we'll oftentimes measure in meters per second. Okay, so let's go ahead and talk about the units for power. And again, try to guess yourself before watching this video. So let's see, units of power. So we know the equation for power is work over time. So we know units of work are going to be joules. Time will oftentimes use a second. So joules over seconds is 1 unit of power. We know work can also be measured in Newton meters because the equation for work is force times displacement. So it could be Newton meters per second. Or the other units that is oftentimes used for power is something called watts. WATTS, which is abbreviated as just a capital W. Be careful when something, and I'm going to just highlight all these different units that we'll use. So if like a number says like something is, like if we look at this light bulb, there's a 60-watt light bulb, keep in mind this W stands for watts. That does not stand for work. So be very careful. It is easy to make silly mistakes with these things. Okay, so keep in mind every machine will have a different power rating. It'll either consume or produce energy at a fast or slow rate. So if we look at different things, so like we know like 100-watt light bulb, the power rating is 100 watts. That means it'll use 100 joules per 1 second. So it'll use 100 units of energy in joules per every 1 second. Lots of different things like dishwasher, that's going to use a lot of power. Mobile phone, not quite as much. DVD player, I guess you all don't use those as much anymore. This is a little outdated. Let's just imagine someone at school, like walking up the stairs, like that's going to be around 250 watts. So all sorts of different ratings. So one more equation, which we're not going to use in this class until like later on in the year, but I want to give it to you right now. So if work is not constant, so if work is not constant, and again, that symbol equals with a no over it means it's not constant. Then power, this is when we have to use our ideas of calculus. Power is going to be the derivative of work with respect to time. So this is essentially like if we were to have a graph of work versus time, and it was something like this, power is going to be the derivative of this graph, which is going to be the slope. So the slope would be power. Cool. We are going to go ahead and solve a couple example problems together. Okay, so now we're going to go involving power or the rate that things consume energy. I have the first two posted here and the other one I'll have out in just a second. So I encourage you to read these problems yourself, try them yourself, and then check back into the video. Okay, so after you've done that, let's look at number one together. So a factory uses a motor and cable to drag a 300-kilogram machine to the proper place on the factory floor. What power must the motor supply to drag the machine at a constant speed of 0.5 meters per second? So we have this is this. So the velocity is what? 0.5 meters per second. The coefficient of friction between the machine and the floor is 0.6. Okay, so anytime we're doing a problem involving forces, we're always going to draw a free body diagram. So what do we have? We have force of gravity, which is what? 3,000 newtons. In this case, the floor will push up the same amount because the y forces are balanced. So Fn is also going to be 3,000 newtons. Let's see. We have the force applied or force push of the machine. Cool. So we have force of the machine, and then we also are going to have force of friction pulling back in the opposite direction. Okay, and our goal is to find power. Okay, so I'm going to go ahead and write down our two equations. So we know our two equations for power are power equals work over time, or power equals force times velocity. So ultimately, either equation will probably work in any case, but let's see which one's going to be easiest. Okay, so we know we have a constant speed of this. Great, and we're dealing with the forces too. Let's go ahead and use this equation. I think it's just going to make our life easier. So looking at this equation, right off the bat, so we need the force of the machine times the velocity. So machine force we don't necessarily know right off the bat, but the velocity is going to be 0.5. Beautiful. So let's go ahead and find the force of the machine. Okay, so let's say find F machine. So if I set up my coordinate system, I know up and down is the y direction, horizontally is the x, and we'll say to the right is positive. So let's go ahead and find that. So let's set up F net x. So we have force of machine, take away force of friction. Okay, F net we know is mass times acceleration. Force of machine we want. Force of friction is always going to be our coefficient times normal force. The mass of the object is 300. Acceleration. Okay, it's moving at a constant speed. So we know acceleration is going to be 0. Equals what? Force of machine. Take away the coefficient is 0.6. And the normal force is 3,000. Cool. Okay, so let's go ahead and finish up this math. So we have 0 equals what? Fm minus, this is going to be 1,800. So the force of the machine is just 1,800 newtons. And keep in mind, because the forces in the x direction, they have to be balanced because it's moving at a constant speed. So the force of the machine is going to be 1,800. Cool. So I can put that in. So 1,800 times 0.5 is what? 900 joules per second, or 900 watts. Great. Let's go ahead and do one more problem. Number 2 is pretty similar to number 1. I'll just post the answer and I'm not going to go through that, but this one should be 60,000 watts for number 2. Let's go ahead and look at number 3 though. So how much energy does a 10-watt nightlight left on for 24 hours consume? Okay, so let's go ahead and look at it. So I'm always going to write down my givens. I think it helps avoid silly mistakes. So 10 watts. Keep in mind the W does not stand for work. That stands for the units of power in this case. So power is going to be 10 watts. Let's see. We're given a time of 24 hours. Okay, and we want to find how much energy does something use. So that is basically we add energy to the system. We do that by adding work to the system or doing negative work to the system if we're taking away energy. So we are essentially finding work in this case. So I know our equation for power is going to be work over time. I just have to double check my units first. So power is 10 watts, and that is in joules per second. So I'm going to need to convert these hours to seconds. Okay, so let's do that conversion. So it's just like 24 hours over 1. So 1 hour is what, 60 minutes? And then, let's see, 1 minute is 60 seconds. Minutes cancel, hours cancel. This will be 86,400 seconds. Cool. So now we can just plug it all in. So power is 10 watts. Work is going to be, that's what we're trying to find, the energy. And this is 86400. Great. So we do some math. And the work or the energy, I'll go ahead. Work is going to be, oh my goodness, okay. Okay, the work is going to, we'll just have to multiply those. So then that's 86400 joules. And so that is how much energy the 10-watt nightlight uses. So I encourage you, if it's like a nightlight or like a cell phone charger, whatever it is, when you're not using it, like during the daytime, go ahead and plug it. Like you'll save some energy overall.